Now that we've learned a lot about what a species is and a little bit about Linnaeus's system of hierarchy, let's look at these familiar animals, including ourselves, and see how they're organized. Well, in a traditional classification of these, showing the relationships between them, we would look at their anatomy, their morphology, their shape. So that this group over here, okay, would share a whole number of similarities different from this group over here. And this group would show different similarities than this group, and so forth. So it's ranked, as you can see. And that is based on the classic observations of anatomy and morphology. Today, people are using molecular studies, particularly genetics, to confirm or to negate those traditional classifications. All the birds have been looked at in terms of the genetics, and it turns out that there were some real surprises, and just because they look like each other doesn't mean they belong in that category. But as you see here, the genetics, particularly, of humans and apes works very well, because you have gibbons out here, which are very different. Then you have orangutans, which are different. And then you have chimps, both the pygmy or bonobo and humans very similar. And then this group, which is separate from gorillas. So it matches identically. So the basic genetics of these groups are now known, of these species, or taxa, we should say, are well known and support the traditional classification. Well, the next thing that we want to consider, and we're going to consider this fairly superficially, is speciation, the process of new species. How do new species arise? Speciation is the most basic process in macroevolution. In other words, when one species evolves into another species, that's a macro change. There are lots of minor changes along the way, of course. And it has been called the mystery of mysteries. We don't see this happening, do we? And we don't see it happening because we live such a short period of time. It takes a considerable amount of time for one species to evolve into another species. And Darwin knew that. And he said, how does one species give rise to a novel or new species? And he said it was the gradual accumulation of small changes over time that ultimately gave rise to a new species. All right? And this is termed gradualism. You start with species A, and over time, after the accumulation of enough small changes, species B becomes reproductively isolated from species A, which means it is a new species, right? We talked about that last time. Okay, so let's look at an example. You got a bunch of monkeys here, and this is known as the core area for the species. Let's say that, that core area encompasses, 5,000 square kilometers or something or other. And because of geological changes, a major river comes along and separates that core area into two areas. And the river, or the mountain that's built between them, is big enough and wide enough or tall enough that it doesn't allow the monkeys in each of those two new areas to continue to interbreed. So they experience what is called reproductive isolation, right? They're reproductively isolated. Now, over the first 10 years, next 20 years, 30 years, maybe 100 years, maybe 1,000 years, maybe 2,000 years, they're still the same species, but there are small changes that are accumulating. Maybe because differences in terms of water resources, differences in the kinds of food, differences in climate, or whatever, and they slowly begin to depart, to diverge into two different reproductive units that are isolated. Living in those different habitats, they experience different selective pressures that lead to different adaptations, right? And what happens is that if that river were to dry up and they came back together, they would be reproductively isolated, which means they could not exchange genes, that they would have speciated, developed into two different species. That's one way that this can happen. An example in Arizona, for example, where the Great Grand Canyon is that there are two different kinds of squirrels, one on the North Rim and one on the South Rim. One is called Sciurus caibabensis and the other one is Sciurus alberti. And they have a common ancestor. Somewhere in the past, there was a common ancestor, which means that there was a core group, and some of them might have made it to the other side and became isolated. And after tens of thousands of years, probably, they underwent a whole series of microevolutionary changes because the conditions on the North Rim and the South Rim were sufficiently different that they crafted a different species. So what would happen if the Grand Canyon filled in and they all were connected again? Probably, if they are genuine species, that is divided by reproductive isolation, they would not be able to interbreed and produce offspring. So there's a living example. Now, there's a great debate that goes on about the mode of evolutionary change. At the top, we see the Darwinian interpretation of gradualism, and you have a nice phylogeny or family tree like this. But on the bottom, it's more reticulated and looks like punctuated equilibrium. The difference between these two is that in Darwin's idea of gradualism, the change accumulates slowly in a lineage, right? And that species arise gradually in fairly large populations. Punctuated equilibrium, which was articulated by the late Stephen Jay Gould and Niles Eldredge of the American Museum of Natural History, said that it is an event. It's not a process. That species arise rapidly in small populations with branching and always produce two species. Well, it's not just a matter of semantics, but one way to look at this is it punctuated equilibrium or is it gradualism? In the bottom chart, it looks like it's gradual. It looks like species A is changing into species B. But at the top, in another area, it looks as if species A is consistent, and then bang, all of a sudden, it's replaced by species B. And that's what punctuated equilibrialists would say happens very rapidly. But could it also be that species B evolved in another area and migrated into that area at the top and replaced very quickly A? It's very difficult to make that distinction. So, moving along, another concept we need to consider is adaptive radiation, which is the rapid expansion and diversification of life forms into new ecological niches. And this is exactly what happened when the dinosaurs died out. And mammals began to diversify and to undergo these adaptive radiations, adapting to new ecological niches. Now, how do we express evolutionary relationships between various species? Well, often people think these are compatible or essentially just the same thing, a cladogram and a phylogeny, but they're not. And I want to show you how the cladogram at the top, which consists of a bunch of branches, and the phylogeny at the bottom, which shows you a number of lineages, how they differ from one another. In a cladogram like this, and you have these different clades or branches, they don't indicate anything about how much evolutionary change or evolutionary time has occurred between organisms like fish, amphibians, mammals, birds, reptiles, and so on. And it lacks exact relationships between ancestors and descendants. We don't have them very carefully outlined here. But in a family tree, what is called a phylogeny. The branches are proportional to the amount of evolutionary change and time. So they tell you something about the amount of time and the amount of change between these various organisms, species in this case. And it also shows very clearly the evolutionary history of ancestors and descendants, and shows you which ones have gone extinct, which ones survived, and which ones were ancestors to certain descendants. So these are not exactly the same. This, in a phylogeny, we're considering the element of time as well as precise evolutionary history of ancestors and descendants.